The Pennsylvania State University College of Earth and Mineral Sciences, Department of Energy and Mineral Engineering presents the Electrochemical Laboratory instructional video for the Daniell Cell, Equilibrium, Galvanic, and Electrolytic Modes. Equipment and materials. A DC power supply, a high-precision ammeter for current measurements, a high-impedance electrometer for cell potential measurement, a variable electronic load for external resistance during power generation, an analytical balance and weighing paper, a copper and zinc electrode with copper wires threaded into them, two 150 milliliter test beakers and two 100 milliliter waste beakers, approximately 80 milliliters of 1 molar aqueous copper sulfate and 80 milliliters of 1 molar aqueous zinc sulfate, a 1 molar potassium chloride aqueous salt bridge, a squirt bottle of distilled water, a variety of wires, alligator clamps, fine and coarse-grained sandpaper. Experimental procedure: open circuit potential or equilibrium mode. We'll begin with electrode preparation. We'll need the distilled water, both electrodes, and 4 pieces of sandpaper, 2 coarse and 2 fine, both cut into approximately 2 by 1 inch strips. I'll demonstrate how to properly clean the zinc electrode. Begin by taking the coarse sandpaper and aggressively sanding off completely the oxidized layer. That is the darker layer that you'll be able to see on the electrode. It's important to take your time here and thoroughly remove all of the oxide layer and as many impurities as possible. Repeat this sanding process for both faces of the electrode as well as all edges that will be submerged in the liquid. It is not necessary to sand the very upper part of the electrode that will not be submerged. However, you may find it useful to press the copper wire thoroughly into the electrode to ensure good contact. Once the coarse sanding is complete, you can wet the electrode using the distilled water and begin sanding while wet using the fine grain sandpaper to get a nice smooth polish. And again, we'll repeat this process on both faces of the electrode as well as around all edges that will be submerged. Next, rinse the electrode thoroughly into the waste beaker using the distilled water and wipe it down vigorously using a paper towel to remove any solid particles that may still be on the electrode. Finally, you may repeat this process one more time using the Kim wipes to thoroughly remove any liquid that may be left on the electrode. This wastewater, paper towels, and Kim wipes are non-hazardous and can be disposed of in the drain and trash. We'll repeat the entire process for the copper electrode using fresh pieces of sandpaper. The solid copper waste is also non-hazardous and can be disposed of in the sink and trash. We will now use the analytical balance to measure the mass of both the copper and zinc electrodes. First, zero the balance with a piece of weighing paper on it. Then place the electrode on this balance, ensuring that the lead will not be touching the glass wall, as well as making sure that the weighing paper itself is not touching the wall. Finally, you may make your measurements. Remove the electrode from the scale and place it on a Kim wipe to avoid contamination. Repeat the entire process using the zinc electrode. Now we will look at the physical cell assembly. The zinc electrode is submerged in the aqueous zinc sulfate and copper electrode submerged in the aqueous copper sulfate. Above them, supported by a ring stand, is the aqueous potassium chloride salt bridge. We will measure the open circuit potential using the high impedance electrometer. First, power up the unit by pressing the red power button in the bottom left. Once the unit is on, press the zero check button located in the top center. Connecting the red and black, positive and negative leads should give a potential of less than 0.25 millivolts. We'll now attach the red positive lead to the copper electrode and the black negative lead to the zinc electrode. Try to stand the electrodes as vertically as possible and separate the beakers such that the salt bridge can be lowered in without direct contact with either electrode or the glass walls. Finally, we can submerge the salt bridge, completing the circuit. Ensure that the porous frits at the bottom of the salt bridge don't actually touch the bottom of the beaker, but instead are suspended in the middle of the solution. Finally, we can record the open circuit potential once it has the chance to reach equilibrium. Electrolytic mode. We will now prove Faraday's law of electrolysis using the Daniell cell. Cell assembly. To the previous cell potential assembly, we are going to add a DC power supply and amp meter. We'll attach the positive lead from the power supply to the copper electrode. The negative zinc electrode will be attached to the black slot on the front of the ammeter, and we will use the white slot for current measurements for the positive lead on the ammeter. That will be connected to the power supply when we're ready to complete the circuit. Before turning anything on, ensure that the power supply's voltage and current knobs are turned all the way to the left. You can power on the ammeter with the power button on the bottom left. Once it is booted up, press the button marked DCI. Next, we can power up the power supply by pressing the power button on the bottom left, followed by the zero check button. We can now prepare the stopwatch. Power up the power supply by pressing the button on the bottom left. Complete the circuit by plugging in the exposed lead to the negative terminal. We now want to force 25 milliamps through the cell. In order to do this, we need to turn the voltage limit up rather high by turning the voltage knob approximately 10 complete turns to the right, and then using the current knob to adjust the actual flow of current. Once a forced current of 25 milliamps is reached, start the stopwatch and begin taking current readings every 5 minutes for a total of 40 minutes. If the cell is assembled properly and all leads are connected, 25 milliamps should be produced by approximately 9 to 10 volts of applied potential. Avoid manipulating the physical cell or touching the leads during this process. After 40 minutes have elapsed, you can turn off the power supply by pressing the power button and breaking the circuit by disconnecting the negative lead from the power supply. We can also power off the ammeter as well as the voltmeter at this point. We can remove all leads. Ensure that the power supply knobs are both turned all the way down for safety. When removing the leads from the actual electrodes, use great caution not to bang the electrodes around into the walls of the beaker, as you might remove some of the electroplated material. Finally, we can carefully remove the salt bridge from the solution by lifting it vertically, again avoiding contact with the electrodes. Once the electronics have been removed, we can carefully remove the electrodes from their solutions. Keep in mind that any waste generated at this phase is considered hazardous and should be isolated and disposed of properly. Remove the electrode from the solution and shake off any excess liquid. We'll then rinse it gently with distilled water Rinse the electrode until you are sure that there is no aqueous copper sulfate left on the face of the electrode. Gently shake off any remaining water into the waste beaker and use a Kim wipe not to wipe down the electrode, but just to wick. By touching the edge of the electrode to the Kim wipe, it will wick the water off of the electrode. Finally, lay a dry Kim wipe on the table and gently rest the electrode to allow the final air drying to complete. Keep the copper sulfate waste separate from the zinc sulfate waste. Next, we'll repeat the entire process for the zinc electrode. Again, keeping in mind that zinc sulfate waste is hazardous and needs to be stored properly. Next, we will reweigh each electrode and record the mass for later analysis. Polarization curve. We will now analyze the voltage-current relationship in the Daniell cell. First, we'll analyze the electrolysis mode. Begin by reassembling the electronics and cell in an identical manner to the previous electrolysis experiment. Power up all the electronics in an identical manner as to before. However, this time, the power supply will be set to provide 2 volts in a potential controlled manner. Be sure to use the readout on the high impedance electrometer for your cell potential and set that to 2 volts, not the setting on the actual power supply. Once the desired potential is reached, allow 1 minute for the cell to come to equilibrium and then record both the cell potential from the electrometer and the current from the ammeter. Continue this process for 3 volts, 4 volts, and so on, up to a total of 15 volts, recording the cell potential versus current. Be sure to allow the cell to generate current for at least 1 minute at each potential before taking the measurement. Continue this process until the cell potential has reached 15 volts, at which point you will repeat the process in reverse, taking measurements at 14, 13, 12 volts, and so on. Once the cell has been returned to 2 volts and the voltage-current relationship has been recorded for the entire electrolytic region up and down, we can power off the power supply and remove it from the system. Galvanic mode. We will now use the Daniell cell itself to generate power and dissipate that power across an external electronic load. We will position the external electronic load in a manner identical to the power supply in the previous electrolysis experiment. Begin by connecting the positive terminal of the variable load to the copper electrode. The negative terminal from the ammeter should be connected to the negative zinc electrode. You can then connect the positive white terminal from the ammeter to the negative black terminal from the variable load. Turn the variable load on by flipping up the power switch on the bottom left. You can then set it to resistance mode by pressing Mode RES for resistance and then pressing the Enter key. Following that, you can set the numerical value of the resistance by pressing res, typing in the number, and pressing enter. For this experiment, we'll begin with 1,000 ohms. The high impedance electrometer is wired up in an identical fashion to the previous experiment. When powering up the high impedance electrometer and the ammeter, use the same procedure as prescribed for the electrolysis experiment. Allow the cell to generate power across the external electronic load spontaneously for 1 minute in order to reach a steady state voltage current measurement. Record those values and then cycle through the following resistances. After 1,000 ohms, measure 200, 100, 50, 25, 10, and 1 ohm, each for 1 minute. Finally, once the 1 ohm measurements have been made, we will bypass the variable electronic load completely to give us the limiting current of the cell. When generating limiting current, it's important to give a little extra time for the cell to reach equilibrium. Now that our measurements are complete, we can power off all electronics and disconnect all electronic wires. Cleanup and hazardous material disposal. Once the electronics have been removed, we can lift the salt bridge out of the solutions. Following that, we will rinse each leg of the salt bridge into its respective waste container. So the leg that was in copper sulfate gets rinsed into the waste copper sulfate beaker, and the same is true for the zinc. Keeping in mind that we should isolate the two waste materials. They are not to be mixed. After this, we'll remove the zinc from the zinc sulfate solution, shake off the excess liquid, and then rinse the zinc electrode into the waste zinc sulfate beaker. Once it has been thoroughly rinsed, we can pat it down with a paper towel and move on to the copper electrode, repeating the process. The zinc sulfate solution that was used in the experiment should not have been contaminated. If it was, it may be disposed of properly. If it has not been contaminated, you may pour it back into the stock solution container that you got it from. When finished with the zinc sulfate test beaker, rinse with distilled water and pour that rinse water into the zinc sulfate waste container. We'll now repeat the process with the copper electrode. Again, shake off the excess copper sulfate, rinse with distilled water the copper electrode into the waste container. Pour the uncontaminated 1 molar copper sulfate back into the storage solution. As long as it was uncontaminated, it can be reused. Rinse the copper sulfate test beaker into the waste beaker for copper sulfate. Once both legs of the salt bridge have been rinsed into their respective waste containers, you can take the potassium chloride salt bridge and return it to the potassium chloride storage beaker and cover with parafilm. Under the sink, you'll find large storage containers for waste copper sulfate and zinc sulfate. Please pour the waste copper sulfate into its storage container, and finally rinse out the beaker with distilled water and pour that rinse into the waste container. Once complete, The waste copper sulfate storage container can be returned underneath the sink. Then the process is repeated with the zinc sulfate. Finally, before exiting the lab, please be sure to refill the carboy with distilled water, refill the squirt bottle with distilled water, and clean all glassware.